The topic for this lesson is diode clipping and clamping circuits. Let's first look at clipping circuits. It is required in some cases to clip the positive or negative peaks, or both, of the input signal. An example is in radio communication, where undesired peaks are created by the presence of noise. These peaks are required to be eliminated for proper signal reception. The circuit used to clip the positive peaks of a signal is shown. This type of circuit is also known as a positive limiting circuit. When the voltage at point A is greater than the battery voltage V sub B by 0.7 volts, assuming a silicon diode, the diode conducts as shown in the second figure. In this case, the output voltage becomes V sub B plus 0.7, and all the input voltage above this level will be clipped. When the voltage at point A is less than the battery voltage V sub B by 0.7, the diode becomes an open circuit as shown in the third figure, and the output voltage is equal to the input voltage since no current flows in the circuit. Diode limiters can also be used with voltage dividers that set the bias voltage as shown in this circuit diagram. The bias voltage is set by resistor values is determined by the equation V sub B is equal to R2 divided by the sum of R1 plus R2 times V sub S. As an example, find V sub B and describe the output voltage waveform for the diode limiter shown in this figure. This circuit is a positive limiter, and V sub B is equal to R sub 2 divided by the sum of R1 plus R2 times V sub S, or 5.73 volts. In the output voltage waveform shown in this figure, the positive part of the output is limited to V sub B plus 0.7, or 5.8 volts. Let's now look at clamping circuits. Clampers add DC levels to AC voltages. They are also known as DC restorers. The figure shown illustrates a clamping circuit that inserts a positive DC level. When the input voltage initially becomes negative, the diode conducts, that is, becomes forward biased, and the capacitor charges to near the input peak, V sub max N minus 0.7 volts, as shown in the figure. Immediately after the negative peak, the diode is reverse biased. This occurs because the cathode has a voltage of close to V sub max N minus 0.7 impressed on it by the charge on the capacitor. Since the capacitor can discharge through the high resistance R sub L, it discharges a small amount from one negative peak to the next. For good clamping performance, the time constant R sub C should be at least 10 times the period of the input frequency. Clamping action ensures that the capacitor retains a charge approximately equal to the peak value of the input minus the drop across the diode. The voltage across the capacitor acts as a battery in series with the input voltage. The DC voltage of the capacitor biases the input voltage as shown in the figure above. If the diode is turned around, a negative DC voltage is added to the voltage as shown in the next figure. This circuit is called a negative clamper. Clampers are often used in television receivers as DC restorers, essentially restoring black and white reference levels which are lost when the incoming video signal is processed through capacitively coupled amplifiers. In the clamper circuit shown, what is the output voltage across R sub L, assuming that R sub C is large enough to prevent capacitor discharge? The clamping circuit establishes a negative DC value equal to the input peak less the diode drop, ideally. Therefore, V sub DC is equal to minus V sub max N minus 0.7, or minus 17.3 volts. In reality, the capacitor will discharge slightly between the peaks, and consequently, the output voltage will have an average value of slightly less than the figure just calculated.